So let's start. বোর্ড দেখা যাচ্ছে?
Yes, sir.
Okay. So today's topic is distribution. Previously, we talk on this events or probability, and then random variable, different type of probability, conditional probability, independency. Then in the last class, we talk on random variable, and now today is a very important topic. It's called distribution. So last class we discussed on random variables. So just a brief recap. What is random variable? Random variable is just a function from omega to r, but still we say it is not just from omega to r. It is there is a sigma algebra. Sometimes this sigma algebra is power set of this omega is called sample space to r, and there again there is a sigma algebra is there. It's called Borel sigma algebra. Something. No need of knowing this thing, what is called Borel sigma algebra. But you just think as the Borel sigma algebra is a power set of R. Basically, it's a power set of R, but not the whole power set. Obviously, not the whole power set, not the all set. So, like this sigma algebra, So this sigma algebra on omega is may not be the whole power set, but this Borel sigma algebra over R, this again is not a whole power set. It's not collection of all subset, but all sort of subset what we we have discussed. This all power set, all subset of real number is included there. Sort of all these intervals are in Borel sigma algebra. All the intervals are there, all the closed, all the open, semi-open, semi-closed, and all this all finite sets are also in Borel sigma algebra. So all open set, all closed sets, all finite or natural number, rational number, whatever. What are the set? What we know that is are in Borel sigma algebra. So give an example of a subset of real number which is not Borel is very tough. This is very tough. So forget about this. So you can just think all sort of known subsets are Borel sigma algebra. So no need of worried about what is not if it is not a Borel set. So just think all the sets what you know is in Borel set. So you just forget about this thing. So this is a real number. So input of this random variable is an element of this omega, what is called sample space. So small omega is the outcome. So small omega is the outcome of this random experiment. That the output is a real number. So it belongs to real number. Such that what we say in the last class, the x inverse of this all sort of this type of Borel set, all open, semi-open, semi-closed, everything is just for example I write half open, half closed, but it may be anything. It's maybe all of both side open, both side closed. This must be a event. This must be an element of the sigma algebra, and this sigma algebra is known in probability is called event space. So that must be event. So any Borel set or any known sets, the inverse image must be an event. So why it is needed? Because if you want to talk about the probability of this set, this x inverse of this set, if you want to talk on this probability of this, so that must be a real number. So this belongs to 0, 1. Now if this set is not an event, then we can't talk about this probability of this set. So if some a function is such a way that this omega, the sample space omega from a real number, such that this inverse image of this Borel set or any open set is not even, then it is not a random variable. So it's just a important part, but you can just forget about all this Borel sigma algebra and Borel set. You just think any if you have any intervals like that, the inverse image of is it even. And if this sigma algebra is a power set of this sample space, sometimes if sample space if it is finite or countable, we take the sigma algebra as the whole power set. If it is a whole power set, that means every subset is a event space event. So that is a no need of this. This condition is trivially true. Then this condition is trivially true, because this inverse image is in sigma algebra, because sigma algebra is the whole power set. So many times we just think sigma algebra is the whole power set. So this condition is trivially hold then. This condition trivially hold. Okay. So again, we just a little bit think on this set. What is this set actually? This is a set. This is actually a subset of omega. But this A and B are two real numbers. So say A less than B are two real number. So this is, you know, these are reals. You know, this is what is this? This is a subset of real number. And what is the definition of this? By definition, any x belongs to this is just x is greater than A and less than or equal to B. That means this is a set of all x in all real numbers, such that this x is greater than A and x is less than or equal to B. So we know this. But what is the definition of this x inverse? So x inverse set of all omega. Now this is, remember this is omega and this is real number. So this is x. So the inverse image, if you take omega from here, you will get x omega here. And if you take any real number, the inverse is just element of omega, the subset of omega, not the element of omega, subset of omega. So let's take this. So x omega is belongs to that set. That's it. So we can write in different way this set. How do we can write? We write it like that. Omega belongs to omega, such that this x omega is between. This is by definition of the interval is this. Sometime we, by notation, this is a notation we write this set as sometimes we write this as x belongs to this. Sometimes we write x belongs to this. So x belongs to this means it is just this set, x inverse this. Or sometimes we write this more easily, or easier notation we write this thing. So x inverse of AB, which is actually this set is we write in this notation. So if I say what is the probability of A less than equal to less than B less than equal to A less than X less than equal to B, that means we want to find the probability of this set, this x inverse A to B. That means we want to find the probability of this set of all omega, such that this happen. And by definition, this is a event. This belongs to the event space. By definition of random variable. If it is a power set, event space is a power set, there is no problem. But if it is not a power set, then we have to take such a random variable that such a function such that this set omega belongs to omega, such that A less than x omega or less than equal to and less than equal to B, this is a event. And then we can talk about the probability of that. So we have this thing. So this is a very important part for random variable. And one more thing, sometimes we write x belongs to this some single element A. This A belongs to R. That means it's the probability of this set X to such that X omega equal to A. Now, this set by notation, we write this set as X equal to A, just X equal to A. So sometimes we call this a probability of X equal to A. So X equal to A means it is not that X equal to A, it's X equal to A. X cannot be equal to A because X is a function. X is a function and A is a real number. How a function can be equal to a real number? If I say function, the sine equal to 2, that means set of all X such that X, all omega such that X omega equal to A. So we just take this notation. Remember, X equal to A, it is not just X, the function equal to A. It means it is collection of all input whose output is A, whose functional output is A. So if I say sine equal to 1, that means set of all X such that sine X equal to 1. And sometimes we write is as X inverse A also. X inverse A. The actual notation is X inverse set continuing. This is the actual, the last one is the actual notation, mathematical notation, and this all are used. Basically, this terminology is used in probability. But remember, this is actually this. By mathematical terminology notation is this, the last one. So now we have this X and we have this different type of subset of real number, and we want to find the probability of X belongs to that subset of real number. Obviously, the subset is the Borel set, in the Borel single algebra. But forget about this thing. All these intervals and this everything is a Borel set. Now, what we actually going on? This is the whole story is like that. There is a random experiment, and from this random experiment, we find a sample space. This omega is a sample space. Then we find we collect some in some subsets, maybe the all, or maybe the not the whole power set. We collect some subset, which is called even space. Maybe this in many times is actually equal to power set, but there are some special situation where we do not take this omega, this script f is as a power set. So this script f is called the even space or the sigma algebra. Any collection may not is not a any collection is not a even space. This collection, if a collection is a even space, if and only if it is a sigma algebra. With that, we know what are the properties of the sigma algebra. So the axioms by what is the definition. Now the story is we have a random experiment first. Always there is a random experiment. From random experiment, there is the story is like that. They start from a random experiment. Everything starts from a random experiment. All this probability, all this calculation, all this anything. If I ask something from find this probability, find that probability, find what is this probability, is this probability is equal to that. The all thing actually start from a random. The story comes from a underlying random experiment. Sometimes you forget this thing, but you should remember there is a random experiment underlying always there. So top of this all this story. You start from if there is no random experiment, nothing is there, no probability. If I ask something, it's find this probability or what is this probability, whether what is why this probability is positive. If I ask this, that means there is a random experience. You should first for any question you should or you first target what is a random experiment. You have to find what is a random experiment. That is the first job to find this all this to answer all these questions on probability. So there is always a random experiment. Unless there is an random experiment, nothing is there. Nothing. So you start from random experiment, then obviously after random experiment we have a sample space, the all set of all outcomes, and then collection of some suitable collection of subset is called even space, or it may be the all subset. In many times it takes all subset is called even space. An element of the even space is called event. So event is a subset of some sample space. So it's a collection of outcomes. So this is the story. So this is omega, and this sum subsets is called. This is the collection of all sum subset is omega. It is F. Now, what next probability came into the picture? So probability is a function from this to 0, 1 with some condition. There is some condition. So we have some from there we find a script f from there script f. So now any subset of omega, we represent that subset as like a point. The point is now a subset of omega. So any point, any element of this script f is a subset of omega. Now we have the function from P to this one. This is a probability. Next thing, and there is a random variable. So remember, so this is the story. First random experiment, then sample space, then event space, then the probability, and then random variable. The function. The function must satisfy some condition. That inverse is this event and such thing. And if you take event space as a whole power set, then that condition is just vacuously or trivially true. Now, this thing. So this is the important part. This is called something called probability space. All this omega, script f, and p. This triplet is the important part. From random experiment, this triplet generates actually. For every random experiment, generate this triplet. And this x actually not only is take a element of omega from to r, is actually this x is mapped is a function which take every element of omega to the element of r, and then every subset to a Borel sigma algebra corresponding, and there must be a corresponding version of this probability in a real number. That probability is probability x equal to 1, and that is called distribution. This probability induced by x. It's probability induced by x. Sometimes called this distribution, not probability. Distribution induced by x. So it's called px. So we have to now check what is px. We learn about this Borel, and then we just forget this Borel because many times we take this script as a power set. So this is very important. This is called distribution. This is called a distribution. This px is called distribution of x induced by p. So if you change your p, the same random variable, if you change the probabilities of the sample space on these events, the same random variable will give a different probability in real number. And obviously, if you change your random variable, then obviously it is changed. So the distribution actually taken care of two things. One, the underlying probability of the that sample space, event space, and this random variable. So that means you have a function from here to here now. Not from R to this. From R we generate say sigma algebra over R. The probability must be a function from sigma algebra. So this is the whole scenario. So there are four things involved. One is omega. Obviously, the random experiment is there. So once omega is there, we find this outward random experiment. We have four things. One is this omega, that sample space, set of all outcomes. Another is set of all events, event space, which is a sigma algebra. May or may not be the whole power set of omega. Then there is a probability from script f to this event space to 0, 1, and there is a probability distribution, what is called probability distribution of x. And there's a random variable where from omega to r there is a function and with some conditions, and there is the last one is the px. What is again this is a probability. So what is the definition of px? So we have to find what is a px. So px is of any set. Now this set is in Borel sigma algebra, so it's a Borel set. So maybe It is a singleton set. That is a subset. Subset. So any subset is not Borel, but Borel set must be a subset. So you take a subset, all known subsets are Borel actually. You take the subset, say interval or singleton or finite set or natural number, rational number, irrational numbers, that you can take. This by definition, this is a by definition. Sometimes by definition we write this, a colon and then equality. Colon and equality means it is by definition it is equal. There are three types of equality. You know there are three types of equality. One type of equality is by definition, and another type is called by notation. And notation and by definition is slightly same things, sort of same. By notational it is equal. So we take notation. By notation, that is that x equal to a. That by notation x equal to a means it is x inverse set containing a. So it is by notation. And one thing is by definition. By definition, this is this. By definition, 3 is 2 equal 2 plus 1. So 3 is equal to 2 plus 1. This is by definition. And another equality is a result. Something 2 plus 2 is equal to 4. The 2 plus 2 is equal to 4. That is equal to, and 3 plus 1 is equal to 4. That is equal to not the same idea. Because 4 is equal to 2 plus 3 plus 1 by definition. By definition, 4 is equal to 3 plus 1. But not by definition, 2 plus 2 is equal to 4. We have to know why the 2 plus 2 is equal to 4. But if someone asks why the 4 is 3 plus 1, you say it is just definition. 3 plus 1 is, we take 3 plus 1 as a 4. But then we can't take 2 plus 2 as a 4. We have to show, we have to prove that why the 2 plus 2 equal to 4. So this equality, so there are three types of equalities. One is by definition, one is that by notationally assign, we assign this thing, and one is just equality. And when you write in computer program, you actually this three type of equalities used there. You sometimes write equal. Sometimes it is equal. So I equal to that, and sometimes called A equal B. So there in computer science, if you just see that all this computer programming very carefully, you actually more in mathematics is involved there, and you will actually sometimes in mathematics we are not that elaborate. But if you want to write a computer program, a code in computer in any language, you need to know all these things elaborately, very carefully. Sometimes in mathematics we just avoid all these things. So I think writing a code in computer language is much more use deeper mathematics there, rather than what you used in mathematics. So this is by definition is this the probability of x belongs to B. If you write more precisely, this is set of all omega belongs to omega, which is actually event by definition of random experiment. This x omega belongs to. So we want to find this probability. So now this is a whole scenario, whole story. What is then we have a sample space, we have a set of events, and we want to find the probability of all these events, whatever, by using random permutation combinations or other thing or other probability calculations. We find this probability of all these events. Then we want to find probability of this that distribution of this random variable using that probability, that p. We know the p. First we know we have to find the omega, then we have to know what is x, script f, then we have to find what is p, then we have to know what is x, what is the random variable, and the last one last job is we have to find the px. So there are 5 things. This R and Borel set of R is predefined. It is fixed. It is fixed for everything. It is fixed for every probability. It is fixed for the whole life. But this omega, script f, px is changing. This is changing. Problem to problem, this changed. But the real line is not changed problem to problem. So real line, what is in the we learn in the class 6 is same in MSc or in whole life. Now this, so we have 5 things actually. Now, what is the last part? Last part, we want to find the probability on the of this random variable over the real number, actually over the not the for all subset, some special subset is called Borel set. Now this is a so what is, if to remember all these probabilities, so the set of all such Borel set, all such intervals is huge. 1 to 2, 3 to 5, -5 to 10, open, close, sort of all type of, there are huge different form type of subset in real number. So to remember to memorize all this subset is tough. That's why we have a interesting function. We introduce an interesting function. Now this is a function from real to real, or real to 0, 1, sorry. It's real to 0, 1. So this function is defined like that for all x belongs to x. We define fx as this p, oh sorry, that must be underlined, x is there. So under that random variable, if we change that random variable, this function is changed. That is this p of this minus infinity to x. This, you know, this interval, what is called, what is this interval? You know this interval. This interval is nothing but set of all y belongs to real number such that y less than or equal to x. This set. So what is this? So again, this is set of all omega belongs to omega such that x omega less than or equal to x. So if someone asks what is the fxx or fx5, that means they ask that what is the probability of the set or the element omega such that x omega less than or equal to 5. So to find this probability, that functional output, you need to know what is the actual the probability on that the event space, and to find that probability, that p, not the px, that p, you need what is the random experiment actually. If you forget the random experiment, you can't find the probability, because all these things generate from the random experiment. The random experiment is changing, then their probability, all this scenario, all this structure will be changed. Now, what is the utility and what is the advantage of this? Now, the advantage is this: from this fx, that function, you can find all the probability of any intervals or anything from there, this function only. And this is what is the important and interesting thing is, you need, for this find the function, you need only one input. Only one input. If you have to know just what is f, say okay, this is f, not fx, it is just f. What is f of 1 or what is f of 2? If you know what is f of 1, what is f of 2, what is f of 0, what is f of -2, what is f of 2.5, if you just know this function, then you can find what is the probability of x belongs to 5 to 3, or 3 to 5, or -7 to 9, or e to 10, some, all these things. All this interval probability you will know. So to memorize that interval probability is tough, because there is a 2 point. There is two input, 5 to 10. You need to know what is the lower bound, what is the upper bound. But to memorize this function is easy, because it's just a function. It's take only one input x. So it's just a function, just real valued function, and this function output is ranges 0 to 1 close interval, and this domain is whole R. And once you find the function, once you know the function, once you remember that function, you get everything. So all this story ends here, capital Fx. So, but once you have this capital Fx, to find this probability, no need of know what is the random experiment, what was the random experiment, what is the random variable, no need to find that. So once all this capital Fx is there, so you can forget all this story. But remember, this finding capital Fx, this needs this whole story, whole scenario. Because if I ask you that this is the random experiment and this is this, and find capital Fx. If I ask you find capital Fx, then this stuff. You have to go through all this story, go through all this, the script f, then x, then p, then px, everything. But interestingly, if I say, okay, your fx is this is the function, your fx is this, Now, to find this probability belong from 2 to 3, this is easy. Now, why this is? Because just if you say if you want to find say probability of this thing, okay, well, A less than. This is just f of b minus f of a. Why this is? This is easy because just f of, by definition, what is f of b? It is the set of all such omega belongs to omega such that x omega less than or equal to b. And what is the by definition f of a? This set of all omega belongs to x omega less than or equal to a. Now, what is the difference between this? So, this is just probability of all x omega belongs to omega x omega less than a minus probability of omega belongs to omega x omega less than or equal to a. Remember, a is less than b. Now, what is this? Some probability of a minus probability of b. What is this? So, if I say this set as a b, this set as a b, and this set as a a. So, b is the set of all omega belongs to omega, x omega belongs less than or equal to b, which you can write in several notation. You can write in this notation, you can write in this notation also, x less than or equal to b. You can write in this notation. So, notationally, you can write anyone. Similarly, if a is omega belongs to omega, such that x omega belongs less than or equal to a, which is you can write in by notation. That is an actual mathematical notation, the first one. You can memorize this something like that, and the easiest way to write this is this. But again, this is x is a function, a is a real number, so it is not that a function is set less than real number. Function cannot be less than or equal to or greater than some real number. That means this set of all omega belongs to all omega such that x belongs to omega, all small omega belongs to capital omega such that all that x omega less than or equal to a. Now, what is this? This is nothing but this probability is nothing but probability of b minus a. Why? Why this is true? Because we know since this is not always true. This is true if a is a subset of b. If a is a subset of b, then only it is true. Then only it is true. If a is a subset of b, then this part is b minus a. This probability is probability of b minus probability of a. It's not that. If it is not a is not a subset of b, then probability of b minus a is probability of b minus probability of a intersection b. So this is probability of b minus a. Now here a is a subset of b because a is less than a. Small a is less than b. Since small a is less than b, this a set a is a subset of b. Some omega less than 5 is a subset of some that x omega less than 5. This collection is a less than x omega less than or equal to 10. Obviously, if it is less than or equal to a, then obviously less than or equal to b. So any element of a is element of b. So it is just b minus a. And what is b minus a? This b minus a is what? B minus a is just a set of all omega belongs to omega, which is in b. So which is in b. So less than or equal to, but not in a. That means it's greater than a. That means this is the probability of b minus a is just probability of b minus probability of a. That therefore the probability of this set this omega belongs to omega such that, which you can write in different notation also. In different notation we write this as a less than x greater than equal to, less than equal to b, which is just probability of a b minus probability of a, which is just probability of b minus probability of a. By definition of this distribution function, this is just fx of b minus fx of a. So similarly, we can find all other probability on the real line, any other set, whatever set you can take, whatever. The finding probability of this that subset, obviously that will be a model. You can just find that probability using just that only one function, fx. So collection of sets, that model set is a huge. And if you always, if you find the intervals, you always take two input. That is just express all this probability in terms of a single function, okay, capital F. So this is the story ends here. Everything is just end in this important function, capital X, which is called the distribution function. This is called distribution function of X, that random variable X, induced by that all this probability is there. All this, this story is there. So once you find this capital Fx, you can forget that px, that induced probability. Now, since it's a function, now it is easy. You can have a functional form of that. You can find a graph of that distribution function. That is actually a different function, have a different distribution name. Something like for binomial distribution has a functional form. It's Poisson distribution, random normal distribution. Every distribution has a different function. Remember, can any function can be a distribution? No, never. Just any function cannot be a distribution function. The properties, obviously, the properties of this properties of fx is we write f. Okay, we write f. Why? If you have only one random variable, you can just write f. If there are several two or more than one random variable, we use fx, fy. Properties. What are the properties? This must be the first property. Properties is this is always in 0 to 1 because it's a probability. Ultimately, it is a probability. That fx is a probability of something for all x. A real number. Now it is interesting. We start with a omega is a sample space. The outcome of a random experiment that may be abstract. That may be head, tail, coin toss, die throw, or maybe it may be any abstract thing. It may be any set of animals, something like that. But we end our story with a random with a real value. Everything is changed to the real value. This random variables do this job. It's change everything. So all these abstract set convert to is a real number. Sometimes we change head to 1 and tail to 0. We change our every student to the registration number, something like that, or roll number. We change a human being to a roll number. That means always our target is we change try to change this all abstract thing to convert to a real number. That's a roll number is doing that job. So roll numbering is actually a function. Is also a function from set of all human beings, all the students from our class or our university to set of real numbers. So given a registration number, given a roll number is nothing. It's just a function. So random variable actually do this job. Now this is the one, and then in tested that must be increasing function. Obviously, is increasing function. Clearly from that the previous thing. If b is greater than a, then fb must be greater than or equal to fa, because the set is now a superset. As x increase, the set is going larger. So probability may be equal or cannot be less. And the other thing is f is right continuous. What is that? That is limit y tends to x plus fx. Oh, sorry, fy is called right continuous. Fx is called right continuous. It may not be left continuous. If it is a discrete random variable, it is not a left continuous. But if it is a continuous random variable, it is a continuous function, also left continuous. And the last, third one, fourth one is very important. If y tends to, or x tends to infinity, fx equal to 1, and limit x tends to minus infinity, fx equal to 0. We just avoid this proof. This proof is not trivial. It involves some real analysis. It needs some real analysis thing. So we just avoid the proof. It needs some deep knowledge of real analysis. Is it tough? It is really tough. So we know a limit. We know what is limit. What is called increasing function. You know what is if a greater b greater than a implies f b greater than or equal to f. This is the increasing function thing, and this is right continuous, not the left continuous, and this extends to infinity fx is 1 and extends to 0 fx is minus extends to minus infinity fx is 0. So this is the distribution function, and if any function which satisfies all these things is now the story is in the reverse way. The story is that you can revert. You can just reverse the whole movie now in the opposite direction. So you can start with just a function. You can just start with a function. Start with f, which has satisfies this. Satisfies 1 to 4. You just take any function. Forget about all this random experiment, all this random omega, that sample space program. Just take a function, which satisfies this 4 condition. And that function, you can show that from that function you can go back. You can find a probability distribution, you can find a probability, you can find a random experiment. You can always find a random experiment such that, again, if you go from that random experiment, you will terminate with that f. So what is the thing? So we start with a random experiment, omega, script f, all such random variables, and we end with that f with some properties, four result, four axioms, for property. We can prove that actually. Now, what is the other way? Other way is if start with the f. If we start with a, we can always go back to that random experiment, random variables, all this probability, all this event space, such that it is not just arbitrary. You take this random experiment. No, you have to prove that if you start with that random experiment, you will end in that f. So what is the thing? If you start with this, you end with f. And the other thing, if you start with f, you can find this thing such that if you start with this, you will end with that f. That's it. Otherwise, I can just say arbitrary. This is my random experiment. This is it. We can always say give an example of random experiment. But we have to prove that that random experiment, if you start with that thing, that random experiment, that event space, we should end with the same f, and this is always true. And this is the important part is if you start here, this f is unique. Once you give all these 4 things, this f is unique to you, but the other is not unique. If you start with f, there are several. You can give a infinitely many random experiment that have the same f. So that is the beauty, that is the important of this distribution function. Because there is a infinitely many different type of random experiment, but there is end with a single f, the same f. And now this is the interesting. Now that's why we are interested on that. Why are you interested on that? See, if you have a say 1,000 many thing, and it's end with a if it's 1,000 many things, and if end with a 10 many part, every 100 is terminated a single thing. That is important because no, you don't remember to the 1,000 many story. You just remember the 10 thing. And once you have this, but in real life we never get that f. F is we create that f from our nature, from our real life experiment. So real life is here. In real life, this is a real life. A real scenario is this. We are in this here. We are always in here. But this is our theoretical part. This is our in our mind, in our book. But once in the real life, we have this omega script a p. We actually want to relate that f, which f actually we have. We already, so we 10 or 15 many f's we read in our class. There are several f actually. Here we just discussing only 3 or 4. Actually there are hundreds f's are there. It's called theory. This is also called theoretical distribution. There's something is called theoretical distribution. We study all this theoretical distribution beforehand in our class, and once we go to the real field, in our research field, in real scenario, real life, then there is no f. F is not coming from the sky. There is a random experiment, and now we have to relate this random experiment, this thing, which f actually can. And if you can relate that f is this f is actually for that whole story. We know that what this f has, what is this? This f has the properties of this f, all this thing, and then we say we know, okay, we know this, so we find all these properties of the random experiment. And there are several hundred many or thousand many random experiments give list to the same f. So this is a whole story of this distribution function. Next class we discuss on this expectations, variance, all these things, and some distribution functions, binomial. And also, there are 2 types of distribution random variable. It's called discrete, and another is called continuous. So today up to this.